So a few examples of tautologies and contradictions. So here we have one proposition P and we have created the formula P or not P. If I look at the truth table, I see that all the entries are true. This will make it a tautology. On the other hand, if I look at the other one, P and not P, here all the entries are false. This will make it a contradiction. So let's see when P implies Q becomes a tautology. So this is the truth table for P implies Q. If you are not sure where this came from, I would ask you to go back to the previous module to see the truth table for P implies Q. Here we had the entry false. Everywhere else we had the entry true. So P implies Q will become a tautology if this case never occurs. So if this case never occurs, then that will be a tautology. The next terminology I'm going to introduce is propositional equivalence. Let's say we have two well-formed formulas P and Q. We say that they are logically equivalent. We write this as P equivalent Q. So this is like equal to sign but with 3 bars instead of 2. If they have the same truth value in all possible cases. In other words, if P is true, Q is true. If Q is if P is false, Q is false. In other words, P and Q are logically equivalent if and only if P if and only if Q is a tautology. We can see an example of this. So we are going to argue that these two formulae, the first one is not of P or Q, the second one is not P and not Q. We claim that these two formulae are equivalent, and to do that we are going to fill up the truth table for each of them, and we are going to see that these entries match. So this is false, 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 this is true, this is true. In other words, both these columns are identical to each other. What I want you to do here is I want you to review why the truth tables are filled the way they are. Make sure that you understand why they are filled out this way, and then verify that these two columns are in fact identical. Here is another example of two formulas that are equivalent. So here we have P or Q and R is equivalent to P or Q and P or R. We can do this by this truth table. So now we have three propositions P, Q and R. So we are going to have a total of 8 entries over here. And we are going to fill out each of these. So we are going to first fill out Q and R, then we are going to fill P or Q and R. We are going to fill out P or Q, we are going to fill out P or R, and then we are going to combine these into this formula. I would ask you to do is fill out these propositions yourself, fill out all the entries in this truth table, and verify whether these two things, these two columns, are identical to each other. Here are some important equivalences that I want you to remember. I'm going to mark this slide as very important because this is something that would be very critical in terms of what we are going to do in the future as well as for the exam. So I have two slides here of equivalences. I will go through each one of them to describe what they are. Most of them are fairly straightforward. There are a couple ones that are something that you may not have seen. So let me begin. First, we have associative laws. The way to think about associative laws is addition is associative. So if I wanted to do P plus Q plus R, I can parenthesis it in any way. And that's exactly what we are doing in these associative laws over here. The only difference is that the operator that we are using is either or and. So the first one is for the or operator. It says if I have P or Q or R, I can do this as P or Q or R. The next one is for and. That's identical. So I will skip over that. The next set of laws that I want to look at are distributive laws. Now, distributive laws are something people get confused over. So I want to ask you to think about what distributive laws you know of. The distributive law that you know of is P and Q plus R is P and Q plus P times R. This is the distributive law that you learned way back in elementary school. The law that we have here is basically identical. We are going to replace multiplication with and, addition with or. We can continue doing the same thing over here. This becomes P times Q becomes P and Q. P times R becomes P and R. So this is what gives us the second distributive law over here. The first one is basically the same thing, but we are replacing multiplication with or. So like this, multiplication with or and addition with and. Otherwise, it's exactly the same thing. Now, in arithmetic, we have only one distributive law, namely multiplication distributes over addition. We don't have the other law, which is basically would be like P plus Q times R, trying to distribute the addition over a multiplication. We don't have a corresponding law in arithmetic. However, in Boolean logic, we have both the distributive laws, that is, conjunction distributes over disjunction and disjunction distributes over conjunction. Okay. The next set of laws, this is something you may not have seen before, is what is known as De Morgan's laws, and this is something that would be very important in terms of what we will do in this class. Many of our proofs will require this. So let's see what this is. This is, if I have not of P and Q, this is same as not P or not Q. The way to think about this is you're going to push the not in. When you push the not in, this is what happens. This P will become not P. The the AND will become OR, this Q will become not Q. In other words, we are going to make every proposition convert it to the corresponding negation. We're going to take an AND, replace it by an OR, and in fact we're going to do the same thing where we're going to replace the OR by an AND. So essentially what De Morgan's law says is when you push the not in, you negate every proposition that you encounter and you swap AND and OR. So you swap conjunction with disjunction and you swap disjunction with conjunction. The next set of laws are tautologies and contradictions. So here we have, this is something we saw earlier, P or not P is true, P and not P is false. The next one is how to get rid of implication operator, and what we have here is P implies Q is same as not P or Q. Among the formulas that I have over here, I would say to you that these formulas are sort of the most non-trivial that you would have expected, and these are the formulas that we would need to use quite a bit in our proofs that we will do later in the class. Now, when we talked about implication earlier, we said implication is hard to figure out. It's somewhat counterintuitive, so that's why I had that big slide that says warning, potential confusion ahead. If you are one of those people, always think of multiplication in terms of this formula. If you convert it to not P or Q, it would be much easier to understand exactly what's going on in implication. Okay, once again, as I said, this slide is what I will mark as very important. Make sure you follow what's going on in this slide, and this is something we will discuss in class if there is need be. This is the second slide for important equivalences. This second slide has equivalences that are in some sense simpler. So the first one is identity laws. Identity laws basically mean that when you apply a particular operator, the value doesn't change. So this is an example where if I apply P and T, I get my P back. If I do P or F, then I get my original P back. So the way to think about this is x plus 0 is same as x, so we call 0 the identity of x, or x times 1 is 1, so we call 1 the identity of multiplication. So here what we have is true is the identity of conjunction and false is the identity of disjunction. We have domination laws. Domination laws basically say if I do P or T, then P essentially disappears, and I get P or T is same as true. False dominates over P in conjunction. That means that if I do P and F, I will get false back. P will disappear. Idempotent laws basically say if I do P or P and P, I get the original value of P back. Double negation says if I negate P, negate it again, I get my original value back. And finally, we have commutative laws that say that P or Q is same as Q or P, P and Q is same as Q and P. Once again, we are at the check before you go ahead slide. I want you to be sure what a tautology is, what a contradiction is. I'm going to ask you to make a copy of the couple of slides that we had in the past that had tables for different tautologies. They will be useful for you during the exams, and you would be allowed to have those pages during quizzes or exams, etc. And this is even for exams that are meant to be closed book. I want you to be able to identify which of these is tautology, contradiction, or neither. And the answer is there at the bottom of the slide. Be sure to do the review quiz for this module, and if there are questions, make sure you ask me or the TA.